All right. Good morning, everybody. Looks like we're still a little light on attendance, but hopefully people will be filing in here in the next few minutes. Don't need these on, I guess. Yeah. Okay, welcome everybody. So please remember the next time we meet, Monday, we will be meeting in person in class. The chancellor of the district, all three community colleges that are in the same district, us, Ventura, Oxnard, and Moorpark. The chancellor sent out an email yesterday confirming, yes, we are still planning to meet in person on Monday. So considering the way things are going, what the UCs have done, what the CSUs have done, what the COVID numbers are doing, it appears that we are going to be in person on Monday. I can't imagine it, realistically, or with any kind of real probability, getting into probability, which is what we're talking about today. I can't really imagine anything happening between now and then that's going to change that fact. So please show up. Please show up. Once we start being in class, remember, there's no Zoom meeting. So if you miss class, you've just missed what we did that day, which is definitely going to hold you back. And once we're in person, I'm going to start doing some things that we haven't really been able to do through a Zoom meeting. So it's really important that you remember to get yourself to campus on Monday, right? And then that you can get into the classroom. And I kind of went over all of that on Monday. I don't want to spend another 15 minutes talking about it. If you have questions about that, please meet with me or read the emails that the school sent you, all that kind of stuff. Basically, get your vaccine card in, be ready to, go through the screening station, get your wristband. Is that what it's called? Wristband. Get your mask ready, stick it in your pocket, because even if you're here and you have the pass, if you don't have your mask, sorry, you got to go. So same with me. I can't be in the classroom without a mask either, and I got to talk for, better part of 2 hours. I don't talk the whole time. But, and by the way, the school had a rule about our Zoom meetings not going longer than 90 minutes. When we are in person, I'm supposed to now stick to the times that are on the schedule. So if you look at your schedule, our class in room 354 is expected. We are supposed to meet from 10 to 11:50. Now, we do have a 10-minute break in there, so sometimes depends on what we're doing. I might skip the break and we get out at 11:40. But basically, we're going to go back to what the schedule says as far as when the class meets. The rule about the shortened class meetings was for Zoom. That I'm not quite sure what they were going for there, but that was the rule. So we will revert to the normal class time starting Monday. So please be there in person. Try to be on time if you can. Give yourself an extra 10, 15 minutes than you normally would, because it's just disruptive when we try to start class and we only have a third of the people there, and then I talk about stuff, and then 10 minutes later we have half the people there. It's just really hard. So please try to get yourself to class a little bit early. Don't pull into the parking lot at 9:58. Try to be there on time if you can. I know it's hard. I'm not used to being out in public in the same way. I gotta make sure I'm dressed properly and all that kind of stuff. Getting there on time, I got to do the same thing. So, now that I think about it, I may have to adjust the office hours a little bit. Now that I think about it. So, so just try to do all that. Okay. When we're back in the classroom, right, bring a mask. I am going to try to, let's see, this is 354. That's a room I can ventilate. I will be opening the windows. So keep in mind what the weather is like outside so that you can dress appropriately. Okay. One of the best things that we can do beyond masks as far as COVID is ventilating the rooms. So having those rooms open so we're constantly getting fresh air means that the viral load in the air, if someone is asymptomatic and breathing out viruses, the best way to deal with that, but beyond the masks, is opening windows and getting fresh air in there constantly, so it's diluting the amount of virus in the air. Some of the stuff we do will be, you'll be in somewhat close proximity to people, as close as you're comfortable. I'm not going to force you to sit right next to someone, but you will want to interact with people. You should have questions on your project. That's a great time to talk to people and go, I'm kind of confused on this upcoming assignment on the project. It looks like you get it. Can you tell me a little bit about it? And then you help each other out. Well, you might want to be closer than 6 feet to someone. So, just kind of be prepared. There's not that many of us, so we can actually spread out a little bit in the classroom. But there is times when you're going to want to work together and talk to people. Some of that comes down to your comfort level, right? I'm not forcing you to sit hip to hip with someone else. But you probably will want to interact with people when we're in the same classroom, okay? So just be ready for that. I'll take roll in a couple of minutes. So yeah, I think that's all I have to say about that. So I'm gonna jump ahead to the probability section because I think we kind of covered what I need to cover out for the correlation regression section. We went through, remember last time I showed you how to do a regression and a scatter plot with the regression line. Okay, you should definitely have one of those in your project. Okay, and a lot of times people look at the project and they look at it like it's supposed to be a professional presentation. And yeah, you kind of want to think about like, well, what if I was a real statistician? How would I present this stuff? But it's not exactly like that either, because this is really a learning exercise. We are not doing, especially with our tiny sample size in this class, we are not doing legitimate statistics, right? Oh, by the way, remember to take the survey. I put the link up there. I originally said when you take your screenshot to have your username in there, but it sounds like it doesn't always show the username for students. So go in there, take the survey, post your screenshot, and I'll get you some points, okay? But our sample size is already going to be small. And that doesn't mean that it's a waste of time. It's a learning exercise, but it's not like we're going to be publishing your results in a academic journal, right? They're not rigorous enough for that. And honestly, like the stuff we're doing is not like, importance level publishable material. So, but it's really good for you to understand what we're doing. It's considered what we would call an authentic assessment. This is the big push right now in academics, is to move away from the old style paper and pencil test, especially when it was online and everyone could just cheat. We're moving towards those authentic assessments and away from old school tests, at least in the class where that makes sense. And in statistics, it makes a lot of sense that we can do that kind of stuff. So just think of the project as a learning experience. Really what I'm grading you on when you're doing the project is, what did you learn? It's your chance to prove to me what you learned over the course of the semester. Okay. So sometimes people think they I should hide all my mistakes. I should, if something didn't go well, I should just pretend like it didn't happen. Disagree. Making a mistake, right? People, like our culture, we're so afraid of mistakes. If I make a mistake, someone's going to call me dumb. If I make a mistake, someone's going to think that I'm not good at this, and they're going to say I'm not good at it, and then I get picked last for the team or the promotion or whatever. Making mistakes is one of the best ways to learn how to do things, assuming that you learn from those mistakes, right? So we have this shame in our culture that when you make a mistake, you're useless, you're worthless, you can't do anything right. That is ridiculous, okay? If you look at people who do things well, you might go, that person never makes a mistake. They're so successful, they just do everything right all the time. That is wrong. You just don't see them when they make their mistakes, okay? Like me, I have a PhD in mathematics. Does that mean that I don't make mistakes when I do math? No, I make mistakes all the time. But I'm trained to the point where I can a lot of times spot my mistakes, and then I fix them, and then I make a mental note like, oh, next time I have to do this, don't do that again, right? But usually that's in private. When I'm doing, when I was a student, it's when I was doing my homework. I would make these mistakes and go, oh, okay, this is how you do it. And then when I'm in class and I'm working with a group, and then they're like, you just know how to do all this stuff. Yeah, because I made all my mistakes at home when no one was looking. And now it seems like I'm just good at all of it. So you can ask people who do research, people who advance things, people who design things. You make mistakes all the time, right? People who sat down and designed the first iPhone. Did they just sit down from scratch, start to finish, and their first attempt was like perfect? No. They spent years going, okay, what if we try to set the screen up this way? Oh, that doesn't work. Okay, what if we set the screen up this other way? Okay, what about when you touch the screen? Do we want haptic feedback? No, we don't want haptic. There's all these different things that they had to go through and try things, and those things didn't always work. So they said, okay, now we got to try it a different way. Okay, so that's part of the learning process. That is literally how you make progress. If you do not make mistakes in your life, that probably means that you're static, you are stationary, you are not moving forward, you are not trying new things, you are not growing, okay? So making mistakes, as long as you're learning from those mistakes, is actually a sign of growth. You are trying new things, you are doing something, you are becoming a better person, right? So don't be afraid of mistakes. And it's the same thing in this class. You're going to make mistakes on your project. Some of you, I put up the survey. The survey's there to take. Some of your questions are bad. Some of your questions are good. That's fine. We went over how to come up with a good question, but you've never created survey questions before. So the fact that you thought you came up with good questions and they're bad, that's okay, right? It's a learning process. It's the first time you did it. It's not a life or death thing. It's that you're going to realize when you get your results back, and not all of you. I'm just saying some of the questions that were put up there could have been done better, right? A couple of them I modified if there was a few things I could do here and there to, oh, I think this is going to help this question come out. But some of them I'm like, I don't know how to fix this question. And you're just going to get results that aren't great. You're going to learn from that, right? You're going to get your results back and go like, oh, now we have to do a bunch of work to massage the data here. I should have asked it this way. If I just put this other couple words in here, we would have got much better results. Okay, that's okay. And that term "massage the data" gets used in it's just a phrase that's used culturally. It means you take the data and sometimes you have to put it in a better form. We'll go over that when we actually have the data, when you've all completed the survey. But it's like, if you ask, I don't know if anyone asked this time, how tall are you? But, you're going to get your answers in a few different forms. You have to go through and put them all in a standard form. That's annoying to do. And the better you ask the question, the less of that kind of work you'll do. I'll show you that, I guess, probably a week from today, we should have all the results from our data, right? Oh, make sure that you have your username and password. When we show up on Monday, I'm trying to book one of the computer rooms so that we can go in and take anyone who hasn't taken the survey, we can get that taken and get that through, just to make sure that we have, it depends how many people we get in the classroom on Monday, but I'm trying to get that booked so that we can make sure we have a few more results. We have so few people in this class that any single person not taking the survey is like it's going to be a major difference in our results. So even if you took the survey already, which I would encourage you to do, please everyone go take the survey today or tomorrow if you can. Even if you're taking it for a second time on Monday, that's actually really going to be helpful. In fact, I'm probably going to have each of you take the survey a couple times because we really don't want to have like 15 results. We want to have like 30, 40, 50 results. It's just going to make everything come out a lot nicer. So have your username and password so that when we go to the beach, which is what we call the area with all the computers, you can log on and take the survey once or twice or a couple times and get that done. Okay? But, so I kind of got sidetracked there. What I was talking about mistakes, like, it's okay to talk about your mistakes in the project, right? Some of you wrote questions that aren't good. But I've had people in their projects say, we thought we wrote good questions. This was a question we asked, and that was a really bad question. Our results were basically unusable. If I was going to do it next time, here's how I would ask this question differently in the future. So a lot of times people are so scared, like, oh, he's going to know that I messed up, and then he's going to mark me down on the project. The opposite, right? What you just showed me with the explanation I just gave was that you learned something. And remember, that's what I'm grading on the project is, did you learn? Do you understand statistics? And if you say, I screwed up and I asked this question about like, what's your favorite childhood memory? And then once I started reading the results that people put in there, I realized, like, what am I supposed to do with this? How am I supposed to analyze this from a statistical perspective? Now I realize that open-ended, long-form answers are not useful in this context. From the next time, I would ask a more closed question with a few options, and I would limit options for people and ask them, maybe what's your favorite season or something like that, where they're picking one of 4 things. But if I'm asking what's your favorite childhood memory, you're literally going to get, if there's 30 people in the class, you're going to get 30 different answers, and they're not quantitative and they're not even really qualitative. What are we supposed to do with that kind of information? If you show me that you understand that difference, good. That tells me you learned something, right? So don't hide your mistakes. Feel free to talk about your mistakes and say, this is where we screwed up. If you tell me where you screwed up in your project, I'm not going to deduct it. I'm going to pay attention and go, did they learn from that mistake? And if you explain to me how you did, that's a good thing. Okay? So that's what we'll be doing hopefully on Monday. It kind of depends but we kind of are going to we're going to have to cheat a little bit, basically. Like the sample size for this class is way too small. So we're going to have to cheat and have everyone take the survey a few times. Now, you might say, well, isn't that unethical? If we were doing legitimate statistics, that would be unethical to have people do that. We are doing this as a learning experience, so it's not, it's not really as bad. And if you want, you could even, your second time taking the survey, like put a different persona on, be a different person. Maybe the first time you took the survey, it was like academic you, who's, very about school and that kind of stuff. And then maybe the next time you take it, it's kind of your like party persona when you go out on Friday and you go downtown, or whatever you're going to do. They answer it from that perspective, right? And then we'll get some different kind of answers in there. You can have a little bit of fun with it. Okay, so what we're going to do today, it's a good time for roll. Let's take that. So what do we got here? This is what, the 9th? Oops. There we go. And I think that some of you will be a little less nervous about the project once you're able to get together. And we will probably, at least every week, and sometimes maybe even twice a week when we meet in class, part of the time will be for you to discuss the project with the people in your group, whether that's the current assignment that you're about to leave a comment on the discussions in Canvas, or whether it is just overall how the project's going. As we get later in the semester, you might ask people like, how are you making the project? Are you using your phone? Are you using screen capture software? Like, what are you doing? And you can all kind of help each other out with that, right? So that'll actually be pretty helpful. Okay, in the meantime, we are going to start statistics. There's a lot to statistics, and statistics is about probability. If you take away probability from statistics, you have very, very little left. Okay, sure, you can still calculate a mean and a median and a standard deviation, and you can still graph a histogram, but pretty much all of the really important tools in statistics are based on probability. And it turns out people do not have a good sense of probability. People's sense of probability is about as good as their sense of statistics. When you know probability, when you know statistics, and you hear most people talk about it, you go, you don't even understand what you're talking about. So it's really important that we understand probability, because probability, you could argue, lies at the foundation of statistics. The real interesting statistical work, the most powerful tools are based on probability. So we need a base level understanding of probability in order to understand what's going on here. And the thing is, sometimes probability is really easy. Sometimes it's really hard. Okay, so just kind of be aware of that. Like, and it catches me off guard sometimes. Sometimes someone will, I'll run across a probability problem, and I've done a ton of probability in my life, right? Sometimes a question will catch me off guard, and I have to stop for a minute and go, okay, wait a minute. How would I think my way through this problem? How would I set this up? And I have to think about it a little bit. So sometimes you get a problem where you're like, oh, this is easy. It takes you 10 seconds to answer the question. And sometimes they're much more complicated. One of the problems is that I think throws people off is those harder probability problems are not always obvious that they're harder. Sometimes you'll read a problem and you're like, oh, this is easy. I know how to do it. And then you get it wrong and you're like, wait, this is super easy. Why am I getting it wrong? But a couple words different in a probability problem can make the problem significantly harder to do, right? And sometimes it's like one word. You insert the word not into a sentence, so you're getting the opposite of it. All of a sudden, that problem is way, way more difficult to do, or you have to use a completely different set of tools in order to calculate that probability. So just kind of be aware. You're going to run across parts of probability where you're like, this is easy, and you're going to run across parts of probability where it's hard. But if you want to understand the things that are coming up later, confidence intervals, hypothesis tests, you're not really going to understand these things if you don't understand probability. And part of the problem is people try to memorize a hypothesis test and a confidence interval, but they don't really get probability, so they're missing some subtleties of those tools. And if you don't really understand the probability underlying those tools, you don't really understand what you're talking about. And it's usually clear in the video when students are talking about it. So we have to get a good basis for probability. And what I will say is, you can use probability in your life, right? People, especially as a math professor, I hear this like, when am I going to use this? Well, the truth is you don't ever have to use math, right? It's like saying, when am I going to use reading? Like, well, you don't have to use reading. Like, you don't have to read. If you don't know how to read, you won't die. Like, you'll still, you'll manage to get food and you'll have a roof over your head. You'll survive to the next day. But it's easy to understand that, well, if I didn't know how to read, though, I would probably, my life would be held back. I probably would not be able to make good choices because I wouldn't be able to read what my choices are a lot of times. I wouldn't know how to do certain things, or I wouldn't be able to do certain things because I couldn't get in there and read my options or read the directions, or, when I'm trying to apply for a school or do something like that. Well, if I can't read, I can't do the necessarily paperwork, right? So people ask well, when am I going to use this stuff? Well, that's up to you, right? People don't read, but they do a minimal amount of reading, like reading a street sign when they're driving down the street or reading a college application. But by and large, people don't read, and it costs them a lot of opportunity and, convenience in their life. Math is the same way, right? There's lots of people who say, well, when am I going to use this in my life? And they don't use it, and they should be using it, right? Probability is one of those things that I use to make decisions in my life, a lot of times like money decisions, right? There's all sorts of insurance out there. There's earthquake insurance, there's flood insurance, there's house insurance, there's renter's insurance, there's car insurance, there's liability insurance, there's tons and tons of insurance. Well, how do you know which ones you should get? Well, what's the probability of those events occurring? In your neighborhood, what's the probability of a flood occurring? What's the probability of an earthquake occurring? What's the probability of a fire occurring? If you understand how to deal with probabilities, then you can start to go, well, maybe it makes sense for me to have earthquake insurance, but because of where I live, I don't think I need to have flood insurance. And flood insurance can be a tricky one, right? It doesn't mean you have to live next to a body of water. It can be that you live next to a large hill, right? Like I do, where, if that hill ever gets wet enough and starts to move, you might have what they call a flood problem now, right? That stuff gets covered by flood insurance, not normal home insurance. So, all these probabilities can help you figure out those kind of events. And also it can help you kind of having a better sense of probability can help you determine when you think a situation is legitimate, or maybe, my little like lie detector is going off here. I think maybe something's kind of sketchy about what's going on here. I think maybe this person just wants me to buy something, or maybe they're just trying to influence my decision. I don't know if I trust what they're saying, because the probability is telling me maybe this person is not being honest, right? And I go, wait, you can use probability to figure out if people are being honest? That's actually a major part of, I mean, it's not perfect, but it's a major part of the underlying tools that we will use for the rest of statistics. So we have this rule right here. And it's important. You need to start thinking this way, not only in statistics, but you can start applying this in your everyday life. If, under a given assumption, the probability of a particular observed event is extremely small, we conclude that the assumption is probably not correct. Okay? So, let's say that we go to the classroom and the desk, the teacher desk at the front of the room is missing, right? The computer, the desk, it's just not there. And we're like, what happened? This was here the other day. Why is the desk and the computer not there? And we're all standing around looking at it. Well, we don't know. Well, we could come up with like theories about that, right? Theories is a big thing right now. We live in a society where sort of conspiracy theories are becoming very popular. Another reason why probability is important, this idea right here. If under a given assumption, the probability of a particular observed event is extremely small, we conclude that that assumption is probably not correct. Okay. So we start coming up with explanations. Why is the desk missing and the computer missing? Well, someone says, well, I think that probably what happens, I know they've been doing some remodeling in this building, and so maybe they took that out because they're going to do some remodeling in this room. Okay, that's one option. And someone else says, oh, I have another option. I think that vampires came in and took it in the night because the vampires need a desk and a computer. That's also an outcome. That could be true, right? Well, no one takes the second one seriously. Why not? Why is the second approach not taken seriously? Why is the first approach taken more seriously, that the school came in and is doing some remodeling in the building and took the stuff out for that reason? Why is that more believable than the fact that there's a cult of vampires that came in and took the computer and desk because they just needed it? Well, it's because the probability of that second event occurring is extremely small. Small to the point where we dismiss it and say that's ridiculous, right? Right? Well, I think aliens came and they needed a computer so they can figure out our technology, so they came and took it. Possible, but like really, really unlikely, right? So you do this on a daily basis. When people tell you things, if the probability of that thing being true, and you don't know the person, I mean, maybe if it's a family member, best friend, you know that person is like trustworthy, they're rock solid, then you give them the benefit of the doubt maybe. But like if someone tells you something and the probability of that thing being true is so crazy small, then you go, I don't believe them. This sounds pretty sketchy to me. I think you're just making that up. Right? So use this every day, but we need to address it because you kind of use it without thinking about it, right? We have this little thing in our brain that goes off, and we're not really thinking in terms of probability. We're just thinking in terms of whether we trust the person or not. But you're going to start making decisions in class using statistical tools based on the probability of an event occurring. And if the probability of an event occurring is low, then we dismiss it because it's less likely to have occurred. Okay, so let's take a look. Basics of probability. So we have a bunch of definitions, unfortunately, a bunch of definitions to get through to, so we can make sense of this stuff. Before we can even come up with definitions and talk about what probability is, we have to do some groundwork first. So an event is any collection of results or outcomes of a procedure. So an event could be me flipping a coin, right? I have got a quarter, I flip it, it's either going to come up heads or it's going to come up tails. Each time I flip the coin, we could call that an event. Okay, I could roll a dice. It could come up, we'll assume it's a standard 6-sided dice. I roll the dice. It comes up 1, 2, 3, 4, 5, or 6. That is an event. I could roll 2 dice at the same time. Sometimes you play a game where there's 2 dice. Sometimes you're playing Yahtzee where there's 5 dice. But when that action of rolling, maybe say 5 dice at once, that could be considered an event. It's one procedure, one outcome of what you're trying to study. So maybe you want to flip a coin 100 times and see how many times it comes up heads, how many times it comes up tails. Well, then each of those coin flips would be an event. Okay. A simple event is an outcome or an event that cannot be further broken down into simpler components. So if I flip a coin and I look at the outcome, I can't break that down into any smaller pieces and still have it be an event, right? It's like flipping a coin. What could I take away? Nothing, right? I roll a dice. Can't make that any smaller, any simpler than it already is. So it's broken down into the simplest component that it can be. So, normally we don't think too much about the simple event. We just think we think about what we're trying to do. We call that an event. Okay. Now this piece, I think sometimes people don't take as seriously as they should. I'm telling you right now, the sample space is hugely important. And this is where a lot of people go wrong with statistics and probability in general, is that they don't understand the size of the sample space. And if you don't understand the size of the sample space, you're not doing probability. You're just sort of like making stuff up. Okay? So the sample space, hugely important. So what is that? The sample space for a procedure consists of all possible simple events. That is, the sample space consists of all outcomes that cannot be broken down any further. Okay, so you're basically making a list of events that can happen. What are the possibilities? So if I flip a coin, my sample space is heads and tails. So there's 2 things in my sample space. The coin's either going to come up heads or it's going to come up tails. One of those 2. Okay, if I roll a 6-sided dice, it's going to come up a 1, 2, 3, 4, 5, or 6. That is what my sample space consists of. 1, 2, 3, 4, 5, and 6. There's 6 things in there. The 6 numbers. Okay, so you're basically breaking it down into the possible outcomes, and it's the sample space is super important. Like I say, if you don't look at and address the sample space, you're not really doing your due diligence as far as good probability. So here's an example. We could talk about single births. Okay, so in the following display, we use F to denote a female baby and M to denote a male baby. Okay, so single birth, you got 2 outcomes. It's going to be a female or it's going to be a male, right? And you could say, well, there's certain, health conditions. We're just going to assume you get put in one of those 2 boxes. So, you have a rare kind of thing that happens at birth. The doctor's going to put you in one of these 2 boxes, either male or female. Okay, so we're simplifying things a little bit. Okay, so a single birth. Your sample space is, there's an F and an M. And this is really smart when you're doing stuff with probability. You want to choose your choice of letters and the order in which you write things in the most organized way you can. Probabilities problems can get out of hand very quickly. You have to be organized with your work, and you have to be clever about choosing things so you don't make mistakes later on in the problem. So here, F for female, M for male. No one's going to mix that up. No one's going to mix it up and later go like, oh, I thought M was females and I thought F was males. I got, because F and M is pretty clear what it is that we're talking about. So, so try to be smart like that where you're picking that. Okay, well, what about if there's 3 births? Well, if there's 3 births, how many outcomes are there? And some people might go, well, there's 6 because that's 3 times how many that you get from a single birth. That's actually not correct. So you're a family, you've decided we're going to have 3 kids. Well, what are the possible outcomes? What is the sample space that you could end up with? Well, you could get female, 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 male, female, male, female, female, male, 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 female, female, male, female, male, 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 female, male, 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 right? And that's in order, right? So we're talking about the order in which you would have the kids. There's 8 outcomes, actually. 1, 2, 3, 4, 5, 6, 7, 8. 8 outcomes. And you might go, well, wait, I thought it would be 2 times 3, which would give me 6. It's actually 2 to the 3rd, which is 8. For each child, you have 2 possibilities. So there's 3 children. For each one, you have 2 possibilities. We're going to learn the multiplication rule here. I think today we'll get to it. We'll see how we do. So it's actually 2 times 2 times 2. Okay, is how we do that. So see how you can sit down and you can create that sample space. Now, this might look unordered to you, but this is actually a very organized way of listing the outcomes for this sample space. So usually what you want to do, if you just sit down and go like, especially as the numbers get bigger and you're like, I'm just going to like make a list. I'm just going to figure them out on my own. These lists can get to be, they can get ridiculously big to where you can't even list them. But, you know, let's just say you're making a list of 32 things. That would be what if we had 2 to the 5th. If we're going to have 5, you're a family, you're going to have 5 kids. There's 32 possible ways in which you can have an ordering of males and females in that way. If you just sit down and try to randomly list them all, you're going to miss some, and you're actually also probably going to double count some because you won't recognize, oh, the one that's 7th on my list is also the same one as the one that's 19 on my list, and you're going to mess it up. So what you want to do is be organized. So the typical way of doing this is you start with one extreme and you work to the other extreme. So one extreme would be female, female, female. All 3 children are female. Okay, so then what you do is you start with the last place and say, okay, what's the other options? Well, if it's not female, 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 the next option for that last place would be male. So then they go female, female, male. See how we're changing the last position? Well, we've now seen all outcomes where it's female, female, blank, right? It's these first 2. So you go, okay, well, now what do I do? Now you change the middle one and go, okay, what if we go female, male, female? Okay, now you change that last position, female, male, male. Okay, that's actually all the ways in which the first child can be a female. So now we go, okay, what about the first one? What if the first child is a male child? Well, then you kind of start over, you know, with the females then. So you go male, female, female. You go, okay, how can I change that last position? Male, female, male. Okay, now we've got the 2 where you go male, female, blank. All right, now what? Well, what about when it's male, male, blank? Okay, male, male, female, male, male, male. Hopefully that made sense, but you'll see as you go through these, if you're kind of paying attention to how they did this pattern right here, you're going to find your sample spaces not only faster than the people around you, you're going to find them more accurately than the people around you. So try to sort of pick up that organized way of writing things. It saves you a ton of time and work when you're doing these. Okay, some notation that we need when we're doing probabilities. So in probability, capital P means probability. Okay, we also sometimes in this class, lowercase p will also sometimes mean probability. I think it's lowercase like on StatCrunch when it gives us probabilities. I think it usually makes it a lowercase p. Okay. What about these capital letters? A, B, and C denote specific events. So written this way, this looks like function notation, doesn't it? Back from algebra, we used to do like f of x. Well, this is p of a, the probability of event A. And you could, it's still literally a function, but we're not going to treat it the same way that we did in algebra with these functions where we would graph the function. Sometimes you'll graph a probability density function, but sometimes you don't. And we're not really going to approach them the same way we did in algebra, but this is technically a function. So P of A denotes the probability of event A occurring. So we might write like, if I'm flipping a coin, you might write P of H. What does that mean? What's the probability of getting heads when you flip one coin? Or P of T, the probability of getting tails when you flip one coin. Okay, so A is that event flipping a coin and getting heads, or flipping a coin and getting tails. We want the probability of that. So that's just a notation you're going to want to be comfortable with. Comes up pretty regularly in this chapter. Okay, so now the bad news, or some bad news, there's different ways of calculating probability depending on what it is that you're calculating. And the biggest thing that you have to look out for is, are all outcomes equally likely? Okay. So that's like number 2 here, this classical approach to probability. So let's do that one first. Okay. So this says that the definition, and again, this is really important that your outcomes are equally likely. The definition is the number of ways A can occur over the number of different simple events that can occur. So it's the number of things that can occur in the denominator, and it's the number of things you're trying to count in the numerator. Okay, so basically this denominator is the size of your sample space. So remember how I just talked about how the sample space is way more important than people think it is? It's because you can't calculate the probability unless you know the size of your sample space. For instance, if I flip a coin, realistically, how many outcomes are there? 2. The coin's gonna come up heads, the coin's gonna come up tails. So there's 2 outcomes. The size of the sample space is 2. So this denominator right here should be 2. Okay, so what's the probability that I flip a coin and it comes up tails? Well, how many ways can a coin come up tails? 1. Okay, so my numerator is a 1. We just said the denominator is 2, so the probability of me flipping a coin and the coin coming up tails is 1/2. Okay, so what does that actually mean? In fact, what is a probability? A probability is a number between 0 and 1. A lot of times you'll hear people talk about probabilities as percentages. We can convert probabilities to percentages, but a probability itself is not a percentage. A probability is a number between 0 and 1. 0 means you're not going to see that thing occur. 1 means that it is basically guaranteed to occur. Most things fall somewhere in the middle, because if something's never going to occur, or something's going to occur every time, we don't really need statistics to study those things, right? Like if I'm at a dartboard and I want to know, okay, I'm going to, there's different numbers on a dartboard. I'm going to throw my dart at the dartboard. What is the probability that I'm going to hit the number 2,437 on the dartboard? It's 0, because there is no 2,437 on the dartboard, right? The probability of that is 0. It's not going to happen, right? Or if something happens every single time, the probability is 1. You don't need statistics to study that. So what if I'm going to roll a dice? Well, how many ways can I roll a 3? Or what's the probability of me rolling a 3 when I roll a single 6-sided dice? Well, how many ways can the dice come up 3? 1. What is the size of our sample space for rolling a dice? 6. So my probability would be 1/6. Okay. What about the probability of me rolling an even number? In fact, let's make it better. What's the probability of me rolling a prime number? Right, because most people could probably figure out pretty quickly, oh, well, the probability of an even number would be 1/2. Okay, what's the probability of a prime number when you roll the dice? Okay, well, there's still 6 outcomes. If I roll a single dice, there's 6 ways that dice is going to come up. Okay, how many prime numbers are there? 2, 3, not 4, 5, not 6. So 3. There's 3 prime numbers between 1 and 6. 1 is not a prime number. So 2, 3, and 5 are the prime numbers. So 3 out of 6, so it's 1/2. If you roll a dice, the probability of getting a prime number is 1/2. Okay. That way we can do it because all outcomes are equally likely. If I roll a dice, the likelihood of getting a 4 is the same as the likelihood of getting a 6. Okay, they're all equal to each other. So that is what we call the classical approach to probability. How do you know when you should use it? Just ask yourself, are all outcomes equally likely? And if so, you can use this probability. Okay, what about relative frequency approximation of probability? That sounds complicated. Relative frequency approximation of probability. What does that mean? Well, okay, imagine NBA Finals or whatever, NBA playoffs, whatever. Steph Curry steps up to the free throw line. He's going to shoot a free throw. And you go, what's the probability he's going to make it? And somebody goes, well, there's two outcomes. He's either going to make the basket or he's going to miss the basket. So there's two outcomes, and the only way he can make it is that the ball goes in the hoop. So the probability is 1/2 that he's going to make it. And you go, but wait a minute. He makes that basket way more than half the time. Where's the disconnect here? Well, it's because Steph Curry's probability of making a basket is way higher than 1/2. So what was our problem in our thinking here? We just used the formula we talked about to apply it to the probability of Steph Curry making a basket. The problem is that the likelihood of Steph Curry making the basket and the likelihood of Steph Curry missing the basket are not equal to each other, right? Steph Curry in his lifetime has shot hundreds of thousands of free throws. He's very good at it. He was, I'm sure he had a natural talent for basketball to begin with, and then he has honed that talent over years and years and years, hundreds of thousands of hours working on his talent and making it that much better. He is way, way more likely to make a free throw than he is to miss it. So in that case, we do not have equally likely outcomes. That's what we just talked about. When I roll a dice, equally likely outcomes. The 2 is as likely to come up as the 5. When Steph Curry shoots a free throw, he is not equally likely to miss it as he is to make it. Okay, so that's why we have to modify things a little bit over here. So then how do we figure out the probability of Steph Curry making a free throw? Well, this is where we have to be a little bit more careful. It's the same basic principle, but we have to be more careful about how we would apply it. And if we're talking about the playoffs, there's kind of 2 ways you could look at it. And you could say, well, why don't we take the number of times that Steph Curry over the season has attempted a free throw, and we'll put that in the denominator, and the number of times that he has made a free throw, we'll put that in the numerator. And then you simplify that, and you could make an argument that that's a good way of figuring out his probability. You can see how it's kind of the same formula as down here, but not really the same. We're actually counting how many times that thing has occurred, not how many ways it could occur. Okay. The other way, you could make the argument that, like, well, you're taking the probability over a whole season. Maybe we should be counting just his performance in the recent playoffs, because that's how he's performing lately, right? This is if you want to have a sports discussion, you could get into that kind of an argument. But then you would just take the number of times he shot a free throw in the playoffs over the number of times that he has the number of times he's made a free throw over the number of times that he's attempted a free throw in the playoffs, right? And that's why on sports, when sports is taking place, if you watch sports very much, they throw around tons of statistics. Why is that? Because they need something to talk about, right? Football takes forever, and there's so much downtime, right? If you time it, the average football game has actually 15 minutes of action, and the rest of it is guys getting up off the ground, and then they get reset for the next play, and then they got to figure out what the play is going to be, and they get set, and then you're waiting for the person to hike the ball. It's like a lot of waiting around with very little action. It's like 15 minutes of action, and then there's 3 hours of just sort of people walking around, getting up off the ground. So they need something to talk about. So they have people literally just pumping out statistics to give the announcers something to talk about. Sometimes those statistics are meaningful. Sometimes they are not, right? And this is why probability is important, right? Because you'll hear, if you listen and you're listening to sports, sometimes they'll have a probability that is reasonable. Like, oh, well, currently in this year's playoffs, Steph Curry is shooting 93% from the free throw line. That's a meaningful stat to know if he's standing at the free throw line. But sometimes, they really get convoluted with it because they need stuff to talk about. And they're like, well, on Tuesdays in a month that ends in an R, if it's this phase of the moon, then Steph Curry is shooting this free throw percent. And you're like, yeah, you can figure out that probability, but it's kind of meaningless because it's just a bunch of like silly, complicated events, right? So you have to keep that in mind, and you'll find a fair percentage of that when you're listening to sports. They're throwing out statistics where you're just like, that's a silly statistic to even be talking about. But they got to talk. They can't have dead air, right? So they're throwing that stuff out there. Okay, so basically it comes down to just ask yourself, are the outcomes equally likely or are they not equally likely? And then you'll know which of the probabilities to use. Step 3 is subjective probabilities. We're not going to get into that too much because that can be kind of tricky. Okay, the law of large numbers, hugely important. Why isn't that in a... That should be in like a box. I thought it used to be. Let's see. The law of large numbers says... Did I miss it? Did we define it up here? No, that's weird. Okay. Again, this is an old edition of the book, so it's a little different. Okay, as a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. The law of large numbers tells us that the relative frequency approximations tend to get better with more observations. This law reflects a simple notion supported by common sense. A probability estimate based on only a few trials can be off by a substantial amount. But with a very large number of trials, the estimate tends to be much more accurate. Think about this in the extreme. What if we tried to figure out the probability of an event occurring with just one trial? I've got a dice. I roll the dice. It comes up a 4. And then I turn around and make the claim, well, I rolled the dice once, and it came up a 4 once. That means that 100% of the time when you roll a dice, it comes up a 4. Well, that's ridiculous. No one thinks that. No one's going to believe that, right? But what did I do? It's because I had such a ridiculously small sample size that my results are obviously silly, right? And that's part of the problem with what we're doing in the project in our class is that we're going to have so few responses. That's why I'm having you all take a few of them, not because that's actually not going to give us better outcomes, but it's going to give you more numbers, and the calculations are going to go a little bit more smoother because you're going to have your graphs are going to look better, and it's just going to be a little easier to do the work that we're working from. So we generally don't want small sample sizes because it's like this. If we have too small of a number of trials, your numbers can be off by a lot. Even think about it. What if I flip a coin 10 times? Okay, we're in class. We all take out a coin. I tell everyone in the class, flip a coin 10 times. What would you expect to happen? Well, you kind of common sense think like, well, it's kind of supposed to come up like 5 times heads and 5 times tails, right? But that doesn't mean it has to. Some of you will flip your coin and you'll get 5 heads, 5 tails. Some of you will flip the coin and get 6 heads, 4 tails. Some of you will flip the coin and get 6 tails, 4 heads. We might get a few people who get 7 of one and 3 of the other, but you would expect to see less of that, right? And you would expect to see even less where one person gets 8 heads and 2 tails, and even less where someone gets 9 heads and 1 tails, and even less where someone gets 10 heads and 0 tails, right? It's possible it can happen, but you probably would expect to see more people get 5 and 5, some people get 6 and 4. You're going to expect to see more of those than the people that you see get 10 and 0 or 9 and 1, right? But would you be blown away if someone flipped a coin 10 times and they got tails 10 times in a row? I mean, it's pretty unlikely, but you're probably not going to like call the news station and be like, you got to know what just happened. This is unbelievable. No, like it's still reasonable that could happen. But what if I had you flip a coin 1,000 times and it came up tails every single time? At that point, you're going to go like, what's going on here? My intuition tells me it should be coming up heads like half the time approximately, but like it's coming up 0 and I got 1,000 straight tails. What is going on here? And then that takes us back to that idea where the probability of flipping a coin 1,000 times and getting tails every time is so unlikely. You're going to start questioning yourself and going, okay, what is going on here? Is this a prank? Is this a trick coin? What is happening here? This is weird, right? So that law of large numbers, you sort of intuitively know it, right? They say common sense in the book, and there's many of us that would argue that common sense is dead, right? Just turn on the news and see the science and everything that's being rejected today, from flat Earth to everything. There's really no such thing as common sense anymore. But I would say it's intuitive to understand that the fewer number of trials you can expect to get probabilities that are not accurate, and the more times you repeat that trial, your numbers are going to more than likely approach the actual probability of something, right? So if I flip a coin once, we are definitely not going to get an accurate reading because we'll say the probability is whatever thing came up that it's 1. But if you flip a coin 1,000 times, that's not going to occur. Okay, so that's the law of large numbers. Sometimes people mess up the law. They misinterpret the law of large numbers. Where is it that they talk about the law of averages? I know they do in here somewhere. And I want to talk about it because it's related to it. Why is it not in here? It's usually right after the law of large numbers. Okay, anyways, we'll talk about it. I'll just talk about it then without finding the definition. So what is the law of averages? You hear people use this. This is the most common thing that people do wrong with probability, is they talk about a thing and they don't know that this is the name. They call it the law of averages. But the law of averages is a misinterpretation of the law of large numbers. Okay, and this is really important because people literally use this to take advantage of you. And people take advantage of themselves. They convince themselves that something's about to happen because of the law of averages, and then they end up with less money than they had a few minutes earlier. So here's an example. When I was young, when I first, the first time I ever stepped in a casino, you could almost miss the roulette table. You could walk right by it, and then unless you were right there looking at it, it just looked like a bunch of people sitting around a table. And then you walk by the roulette table and you go, oh, that's a roulette table. There's like the number layout, people can place their chips on a number, and then you've got the spinning wheel that goes around and around. The marble goes around and around the spinning wheel, and then the ball lands on a number, and if your chips are on that number, you get paid. Okay. If not, then they take your chips away from you. So you could walk right by it before, and if you weren't looking, you might not even realize it's a roulette table. Now you can't miss them in casinos, because what they do at the roulette table is they put a giant sign up there that shows the last events, right? Maybe not at the high end, because the high-end people, if you're betting at a high-end roulette table, then this probably isn't going to work on you. But it works on a large number of people walking through a casino. They put a sign up there, and it shows you what numbers have been coming up, and it shows you the color. Because on a roulette table, you can bet on either there's slight variations from casino to casino, but usually there is, I forget how many numbers it is, but there's a bunch of black numbers, there's a bunch of red numbers, and then there's 1 and sometimes 2 green numbers, right? So what happens is when people walk by is they see like, oh, the last 7 times that ball has been rolled, it came up black. That must mean that it's about to come up red, right? Because the law of large numbers says that as you repeat a procedure, the outcomes are more likely to approach the actual probability. And I know the probability because of the greens, the probability of a black number coming up is slightly less than 1/2, and the probability of a red number coming up is slightly less than 1/2. So they go, well, if a black number came up 7 times in a row, that means red is due. Like, you literally hear this in casino talk. Like, it's due. It's ready to hit. That's no such thing. Like, that doesn't occur. But that's the law of averages. They're not interpreting the law of large numbers correctly. The law of large numbers doesn't say that the probability has to get made up for on the next turn. It just says eventually. If you do 100,000 events, you're likely going to see the true probabilities come out. It doesn't mean that it has to make up for it the next time around. So people will see, 7 black numbers in a row have come up. I'm putting my money on red because they're like, it's due. It's ready to hit. Okay. But that doesn't work. If you think about the way the universe works, and depending on your own, ideas, you probably everyone has a slightly different way of viewing this. But the reality is there's nothing in the universe that is, besides the laws of physics, that is dictating what that little marble is doing. The marble doesn't have a memory. Like, the marble, when it's spinning around the wheel, doesn't go, I've landed on a black spot 7 times in a row. I better make sure to land on a red spot this time. Like, that's not a thing. The marble doesn't have memory. The universe is not, like, remembering how many black numbers came up and it better come up red this time. It doesn't work that way. Just like when you're flipping a coin, the coin doesn't have a memory that you just got tails 9 times in a row. Well, to make up for it, it better come up heads on the next time. The law of large numbers is talking about real large numbers, which says if I flip a coin 100,000 times, we expect the outcomes to be roughly 1/2 heads and 1/2 tails. It doesn't say that it's got to make up for it right away. Okay, so that is one way in which, since casinos started doing that, their money at the low-end roulette tables has, like, skyrocketed. They make so much more money now because they get people who would never bet on roulette walking by and doing incorrect probability. They're literally using your inability to do probability to trick you into playing their casino game. Okay, so you walk by and you're like, red's about to hit. I'm putting my money on red, but in any event that has equally likely outcomes, the probability does not change for a single event. So if I flip a coin 10 times in a row and it comes up tails, what is the probability that it will come up tails on the 11th try? It is still 1/2. It doesn't change. The coin doesn't have a memory, and the universe is not trying to average things out. Okay, so the law of averages is false. So when you're walking through a casino and you see that there, you can kind of laugh to yourself and go, they're trying to trick me with the law of averages, but I know the law of averages is incorrect. I'm not going to get suckered into putting my money on the roulette table. And if you want to put your money on the table, go ahead, but don't do it because they've convinced you that red is due or black is due to hit. It doesn't work that way. Okay? If it did work that way, the casino would not be telling you that. Right? They wouldn't be showing you like, you could win. You're about to win if you bet on this. They wouldn't want you to bet on it because you're going to win, right? So that comes up a lot, and you hear people use the law of averages all the time, and it's like sometimes it's just not worth it, but you want to like explain like you don't actually know what you're talking about. That's not how probability works. So you want to be careful about that, okay? Let's see, where are we? How we go? A little bit of time. Oh, speaking of this, stuck in an elevator. What is the probability that you get stuck in the elevator in your next elevator ride? I mean, I don't even want to talk about the probabilities. Just a heads up, the science building of which our classroom is in is notorious for the elevators getting stuck. If it's possible for you, take the stairs, right? Numerous faculty have been stuck in the elevator. The night of the Thomas fire, someone was stuck in the school elevator. They didn't even know what was going on. They're stuck in there for a few hours. No one knew it. They were like, finally they heard like a cleaning person, so they yelled out. They got the person out of the elevator. The person didn't even know, like, what? The city's on fire? What are you talking about? So it's just, if you can, some people can't, and then, you do what you can. But if you can take the stairs, I would recommend it. The building that we're in is not a great building. It was built in 2000, so it's not that old as far as buildings go, but they've actually slated it for destruction. It's the current building plan for the school has planned in the next 5 to 10 years that the building we're in will actually be demolished and rebuilt because it's such a disaster. So I'd stay out of the elevator. Okay, where are we? Oh, simulations. We'll actually do that in StatCrunch, where you can see how those. Sometimes you can use a simulation to, if you have a really complicated probability that you're trying to figure out. Sometimes the quickest way to do it is just where you simulate that event happening, 100,000 times or 1,000,000 times, depending on how much computing power it's going to take. You can actually get to a situation where if there's enough computations, 1,000,000, and you repeat it 1,000,000 times, it might take a couple hours for it to finish or more. But a lot of times you can do 100,000. If it's rolling a dice, you could easily do 100,000, and it would still happen so fast you might not even really recognize that there's an issue or that that the computer's slowing down. So let me show you how to do that in StatCrunch. So if you go into StatCrunch and it's got, let's see, I thought it was under here. No, oh, here it is, simulation. So you go applets. Can't quite see it on the screen, but it says simulation down here. So I go to that, and then let's do coin flips. So this allows you to simulate massive numbers of coin flips. So let's take a look at this. You could even change the probability. So you could say, I want a coin that is going to come up heads 75% of the time and tails 25% of the time. You could do that, but we don't want to do that because we're kind of just wrap our brains around probability right now. So we'll tally the number, tally heads and tosses, and then it picks a random number. Random numbers in computers are actually more complicated than people think. If you're going into computer science, you'll learn all about that. But for now, let's just compute it. And it says, okay, here is our simulation. Let me move this so you can see it all. So basically, am I going to get this? This isn't really fitting on screen. There we go. Kind of like that. Okay, so I could do one run at a time. Now, this was a fair coin, so I want to flip the coin 5 times. Let's do 5 runs. So I'm going to do 5. Okay, 5, and you can see each outcome coming. Okay, so we did 5 outcomes, and we got 3 heads and 2 tails. So that would tell us that we're expecting 60% of the time we're going to get heads, and 40% of the time we're going to get tails. And we go, wait a minute, that doesn't sound right. Let's try it again. Let's reset and do 5. Oh, this time it's telling us that 60% of the time we're going to get tails, 40% of the time we're going to get heads. And we go, wait a minute, why are we getting these different numbers? Again, we're not really making use of the law of large numbers. We're doing too few trials, too few samples. So let's look at it this way. If I reset and do 1,000 runs, there, it just that fast, it did 1,000. See how the numbers came out a little bit better? Now it's saying 49.5% of the time you're going to get heads, and 50.5% of the time you're going to get tails. See how those numbers are closer to 0.5 and 0.5? Closer than what we did when we just did 5 runs. What if we keep doing them? Watch this number here. We would expect that to be getting closer to 0.5, right? So watch as I do more runs. So 1,000 at a time. There, now that number's really close to 0.5, right? And now it's going to vary a little bit, but see how it's getting real close to 0.5? That's the law of large numbers coming into play, saying as I do more and more of these runs, we're now at 13,000. See how it's pretty close to 0.5? And if we sat here and did this, all day where it's 100,000, we'd see that number getting closer and closer. It doesn't exactly get closer every single time we run a trial because there's always a little bit of randomness in there. But see how we're much closer to 0.5 than we were when I just rolled the dice 5 times? So simulations can be really helpful with that. Or sorry, this was flipping a coin. We can do They also have a simulation for, they've got what? Birthday problem, coin flipping, dice rolling, poker hands, raffle winning, and urn sampling. I don't remember what urn sampling is, but let's do dice rolling. So six-sided dice. Those of you who play Dungeons and Dragons, you could put your, your D8s and your D20s and stuff like that. You could change this to be that kind of a dice if you wanted, and you could play around with that. And you could do it here. Okay, we've got a dice simulation. Our outcomes are 1, 2, 3, 4, 5, 6. That's our sample space. And then we want to know the frequency. So let's do 5 runs. So we did our 5 runs, and look, man, it looks like we got 6 40% of the time, and we got 4 40% of the time. But that would be ridiculous for us to go, well, anytime you roll a dice, you're going to get 6 40% of the time, and you're going to get 4 40% of the time, and you're going to get 5 20% of the time, and you're never going to get a 1, 2, or 3, right? It's because we were irresponsible and only did 5 trials. So what if I do 1,000? Now all of a sudden you're starting to see these numbers leveling out, and the proportions are more likely. There's always going to be a little bit of variability, because if you flip a coin 1,000 times, it's not, it's possible, but you're probably not going to get 500 heads and 500 tails exactly. There's going to be a little bit of variability in there, but it will be really close to half the time heads, half the time tails. Okay? And as we keep running this up, you can see, yeah, those are getting more and more level so that they're about the same outcome. Okay? So that's important. That law of averages, don't fall for that, right? Here we go. The probability of an impossible event is 0. The probability of an event that is certain to occur is 1. Now, it's a little oversimplified. Those of you who go on to learn more probability will learn that it's a little more complicated than that. But that's a good way of thinking about it at this level. If the probability is 0, a thing can't happen. If it probability is 1, it can happen. And they've got even a chart here, right? So if your probability is 0.5, that's about 50-50 chance. If it is impossible, you're at 0. Little bigger than 0 just means it's unlikely. Certain to happen means you're at 1. And very likely means you're a little less than 1. Okay? Let's see. Do we have time to get into this? Yeah, I think we do. Oh, right. And for any event, let me move this over. For any event, the probability of A is between 0 and 1 inclusive. That is, the probability of an event has to be between 0 and 1. Okay? Sometimes students don't catch this. And they'll do something, and they'll turn in a problem, and they'll go, oh, the probability of this is 1.75. You can't have that. If the probability of something happening being 1 means that it's guaranteed to happen, well, then what would a probability of 1.75 mean? Right? It doesn't make any sense. So when you do a probability, you always want to double check. Is this a number between 0 and 1? If it's not, then you have made a mistake. Okay? And we'll get into those kinds of mistakes. We only have a little bit of time left here, but we'll get into those mistakes here in the next few minutes, and then we'll see how far we get into it on Monday. Monday is going to be kind of a weird day because it's our first day back. So we'll kind of see where we go with that, but I'll talk more about that. So complementary events. Complementary events tend to be confusing to students, but hugely helpful when you can do it, right? Sometimes what happens is you'll be trying to calculate a problem, and it's going to be really hard to calculate. But if you calculate the complement, that is the opposite outcome, it's really easy to calculate. So if you think about it, like, what if you roll a dice? Okay, we already talked about what is the probability of rolling a 6 when you roll a 6-sided dice. Well, the probability of rolling a 6 on a 6-sided dice is 1/6, right? The sample space is 6. That's the denominator. The ways in which you can get a 6 is one way. The dice comes up 6. So the probability is 1/6. Okay. Well, then what if I asked you, what's the probability that I roll the dice and it doesn't come up a 6? In other words, it comes up something other than 6. Well, you could calculate the probability of getting a 1, the probability of getting a 2, the probability of getting a 3, probability of getting a 4, and the probability of getting a 5. And then you could put those probabilities together. Or you could think about it in terms of the complement. So if the whole sample space has to add up to 1, the whole probability space, I should say, not sample space, the whole probability space adds up to 1. That is, if you take all the possible outcomes, in this case, like with rolling a dice where the events are disjoint, and you add them up, they add up to 1. Well, and that's how it works with the dice, right? Like, you have 6 events and none of them overlap with each other. If you roll a 2 on a dice, you didn't get a 3. If you roll a 5, you didn't get a 6. Okay, so this means we don't have to worry about overlapping events. Like if I said, what's the probability of rolling a dice and getting a 2 or getting a prime? That one's harder to count because 2 goes in both of those categories. 2 is a prime, and it's also an even. Did I say even? It's even and it's prime, so it goes in both of those categories. That's harder to count. But if we're just rolling the dice and saying, what's the probability of it not coming up a 6, we don't have any of those overlaps. So what you can do is say, well, if the whole probability space has to add up to 1, and I know that getting a 6 is 1/6, then if I take 1 minus 1/6, my probability of not getting a 6 should be 5/6. Should be 5/6. The leftover. It's 1 minus 1/6 would give you 5/6. Okay. And there should be one on here. So you'll go over that when you're. Oh, and we call the complement event. We put a little line over the top, right? So just be aware of that. You'll do some problems based on that. You'll see it in the homework when you do that part. We're not going to have to worry too much about odds. Not going to come up too much when we're talking about statistics. Okay, the odds don't come up too much, so I'm not going to like worry too much about the odds. In fact, odds come up a lot of times with gambling, right? Now, why is that? Well, probabilities are really easy to understand. Like, would you bet on something where you knew you had, like, you were only going to double your money? So, you bet on a game, maybe a sports game. You bet $50, and if you win, you get $50. If you lose, they keep your $50. Okay? But what if you knew the probability of winning was only 40%? You're like, well, we'll talk about expected value. But if you calculate that in an expected value, that means in the long run you lose all your money. Okay? So you wouldn't make that bet because you'd go, well, all I do is double my money, but I'm more likely to lose than I am to win. So that means in the long run I lose my money, which is actually how casinos do that. They don't tell you the probability then, but they will tell you the odds. Because if you have sometimes if you have the odds, it's a little harder to calculate. Like you have to like odds are not as straightforward, so you have to think your way through if what you're looking at makes sense or not. And a lot of times it does not. So you almost never will see a casino give you the probability of winning, but they will sometimes give you odds because it's not as obvious that it's not a good bet. But if you think about it from the casino standpoint, like everything is in favor of the casino, right? Because if they were equally likely to win as to lose, then they would never make money. But if you think about it, like casinos cost a lot of money to run, right? You got all these people working at the casino. You got all the lights going all the time. You got all the stuff making sound. They got machinery, people fixing the machinery. They're cooking food and like doing all sorts of stuff. What's paying for all that? Well, it's the money that the casino is taking from people. So really, every game in a casino has a slight edge, right? They set up the rules in the game, so there's a slight edge to the casino. So if you, in other words, if you play long enough, you're going to give all your money to the casino. Because even like, it's harder to find this now, but like if you can find tables where it's like old school blackjack, then it's real close. It's like 51% that the casino is going to win, 49% that you can win, assuming you play perfectly. But even then, if you play long enough, they get all their money. They don't care. Like, you ever wonder, you're at a casino and you're like, man, that guy just won like $20,000. Aren't the people at the casino like mad? They just had to pay out all that money? No, they're fine with it because they know they're going to get it back later. Because if you're playing a game where the other person has a slight advantage, they're going to win 51% of the time and you're going to win 49%, then eventually all the money ends up with the casino, right? So if you could play, if you show up to a casino and you go in there and you're like playing for an hour and maybe you're up $300 or something, and then you leave. Okay, well, you got that $300 and you left with it, but that's not what people do anymore. People go to Vegas and they're there for the weekend. So what are you going to do? At the end of the first night, you're up $300. Are you just like, okay, guess I'm done. I'm going to keep my $300. No, you went to Vegas, assuming I'm not one who takes Vegas vacations, but assuming you're going to Vegas for the weekend, you're probably going there to gamble. You're going to keep gambling, and they know that. That's why they want you to stay in the hotel, because then you can't leave. You're kind of stuck there for a few days, right? And sometimes they'll even comp your hotel or give you a big discount on it because they don't really care about making money off the hotel room. They want you downstairs gambling. And if you've bought 3 nights at a hotel, you're going to gamble. Where are you going to go, right? It's not like there's that much stuff to do in Vegas. Like I've been to Vegas enough times. I have family there. They're like, there's plenty to do, but the big thing people are doing is gambling. They know. They don't care when you win and when you lose. That's why they don't get upset, because they know if people play long enough, we get all the money back, right? So just kind of realize when you walk into a casino, it's a great chance to just look around and try to understand probabilities, right? It all starts to make sense, and you're like, oh, that sign over by the roulette table, I'll just ignore that. And, there's lots of stuff that's directed at people who don't understand probability. Okay, so let's end there. A couple minutes early. Another reason. So we'll end on that section, but the way they start this chapter is with a question on lie detectors. So this is a good just a good discussion. Like, why is probability important? Well, a lot of times when you hear about a lie detector, you go, well, it detects lies. But if you think about it, like, is it a magic box that somehow knows everything in the universe, and when you tell something that isn't true, the magic box knows that you told a lie? No, that's not how that works. The way a lie detector works is it's actually measuring your body's response. Okay, so it's checking moisture level on your skin. So if you start to sweat, it detects like, oh, you're, not that you're dripping sweat, but like, your body puts out a little bit of moisture because you're getting nervous and your body sweats a little bit. When you're nervous, your heart rate goes up a little bit. You have physiological responses. Your body responds to that. That's what we do out on the, before we formed cities and stuff like that, and you're walking through the jungle, and all of a sudden you think there's a tiger a couple trees away. Your body starts getting you ready to deal with that tiger, right? It makes you nervous. You start, your heart is beating so that you can run or fight or whatever you have to do. Your body has these responses that are sort of beyond your control. And what they have found is that when a person lies, they get a little bit uncomfortable, and those same things occur. You sweat a tiny bit. Your heart rate goes up. These kind of physiological responses take place. So, the idea behind a lie detector is that when you tell the truth, you should be relaxed and calm, and so your heart rate will drop. But when you tell a lie, your blood pressure and heart rate and that kind of stuff are going to go up a little bit. So it measures that. Well, if you think about it, if the FBI shows up at your house and says, we want you to take a lie detector, you're probably going to be a little bit nervous, right? You're going to be nervous anyways because you're like, wait, I don't think I did anything wrong. Why is the FBI talking to me? And like, why are they hooking me up to this test? And if you did commit a crime, it's even worse because then you're worried that you're going to get caught, right? So the reality is most courts, lie detectors are inadmissible. You can't even admit them because science has shown like they're not a magic box that tells when lies have occurred. It's an indirect way to tell if people are nervous. And yes, sometimes you get nervous when you're lying, but have you ever been nervous or scared or have anxiety when you weren't lying? Yeah, you're human. We all have. We've all been scared or nervous in situations where we were being honest, but we still was a bad situation. So lie detectors are actually not very accurate. So, you'll hear about a case where you're like, well, so-and-so denied taking a lie detector test. And then you think, oh, well, they must be guilty because why wouldn't they take a lie detector? But if you stop and use probability and you think about it and you go, actually, the probability of a lie detector accurately detecting lies is kind of not as high as we would like to think it is. You realize, like, oh, well, there's things that could go wrong, right? And this is actually a good example to talk about the ways in which things can go wrong, right? What are the outcomes if you take a lie detector test? Well, let's say you're asked a question. There's two outcomes to your response. Either you tell the truth or you lie. But there's 4 total outcomes for the whole problem. That is, let's say that you tell the truth and the lie detector says you tell the truth. Oh, that's good. Then it worked properly. It was accurate in that case, right? You told the truth and the lie detector determined that you told the truth. What if you told the truth and the lie detector determined that you were lying? Uh-oh, now you're in trouble with the FBI. That's not good. And it's weird that some of these enforcement agencies still use lie detectors, since if they're not admissible in court, that's a pretty good indication, like, they're not very reliable. So why are they still used? It's kind of a coercive tactic that gets used. But okay, so you can tell the truth, and the lie detector will either say you told the truth or it will say that you were lying, even though you did. Even though you did tell the truth, the lie detector says you're lying, and now you're like, uh-oh, now I'm really in trouble. Okay, what's the other possibility? The other possibilities are that you tell a lie, and the lie detector thinks you told the truth. Oh, good. I'm actually going to get away with this, or if so that's a possibility. Or the fourth possibility is that you lie, and the lie detector says you're lying. So that's 4 outcomes, only 2 of which were accurate, right? The 2 where you told the truth and it says you told the truth, and the one where you lied and it said you lied. But there was also where you told the truth and it said you lied, and there was the one where you lied and it said you told the truth. Now, those outcomes are not equally likely, but it helps to understand, because most people go, oh, well, there's only 2 outcomes to a lie detector. Either it's right or it's wrong. There's actually 4 outcomes. You have to look deeper at 4 possible outcomes and realize, like, there's a couple ways it can be wrong. There's a couple ways it can be right, but there's a couple ways it can be wrong. And when you start looking at the numbers, you just realize, like, I'm not taking a lie detector either if anyone ever asks me to take one, right? So, probabilities can help us dig deeper into these kinds of scenarios and understand them at a better level, okay? So, and you'll do that in some of your homework. You'll look at the ways that a thing can be right or wrong, and you'll come up with these kind of outcomes because it's important from a probability standpoint. Okay, we'll end there. Make sure that you realize we are meeting in class the next time. Be ready to go with that. Be all ready to get into class. That is, make it through the screening and all that kind of stuff. And then be ready to use a computer. If I can get us booked in a computer lab, then be ready to use the computer, because we'll probably have everyone take the survey maybe a couple times. I changed the settings so that you can take it multiple times. That way, even if we're kind of faking the data, it will be better for you to have, like, if we have 40 or 50 outcomes, that's going to be better than having like 12. Okay, so be ready for that. I will be in Zoom. I'll stick around if anyone wants to talk to me in Zoom. Otherwise, I will see you in person on Monday. And thanks, everybody. We'll talk to you later.